Hello, everyone. Today is our fifth lesson from the series of lessons, computational molecular materials design for newbies. By newbies, I mean the kids from high school or undergraduate students who want to know how to operate computational materials design program, which help to build atoms, molecules, and crystals from atoms. So today we'll be talking about the symmetry of crystals, and we will be using the program SageMD, which I already told you about in one of the previous lessons. And I will show you several examples of the crystals and show what their symmetry is. So obviously it's quite a complicated subject to know all about the symmetry of crystals. So I will only make you a first short introduction, and then you can find the other videos on YouTube, reading materials on internet and the books. So crystals possess the so-called point symmetries and translational symmetries. So by point symmetries, we mean the rotations, reflections from the planes, and inversion near the center symmetry. And correspondingly, translation symmetry is operation which multiply elementary unit cell of the crystals, which contain all information about of the crystal itself. All right. So by the way, the first things what you know about symmetry is your own reflections in the mirror. So that's an example of symmetry. However, keep in mind that when you see your own reflection in the mirror, that's not exactly you, because your right hand is becoming left hand and your left hand is becoming the right hand. So, and obviously your heart is on the right side. So it's because we don't have a symmetry of this type. So in a sense, you don't see exactly yourself. So, all right. So what about the crystal symmetry? There is several type of symmetry of the crystals, which defined by the relations between their parameters of the unit cells, unit cell vectors and angles. So there are 7 types of this: triclinic, monoclinic, orthorhombic, tetragonal, hexagonal, which also has inside of its trigonal symmetry, and cubic. So with program SageMD, I will give you example of several structures, several crystals, and show what the symmetry is. So let's go, let's do the screen sharing. So let's go back to the website of SageMD program. So you can download program from SageMD website. Here's the address, sagemd.com. The program is free and it works on Windows and Linux system. So you can download it and it has a big database of crystals, which I downloaded a few examples to show you some samples of crystal symmetry. So let's go now and open the SageMD program. All right, so I prepared a few examples and I'm going to show you them. So first example, oh, by the way, I use a Russian version, so but you can easily find the correspondent if you use English version. So okay, first example is structure of gold. Okay, so that is unit cell. If you look on the unit cell, you may think that the atoms have only 3 neighbors, but it's only in a unit cell. So if we multiply the unit cell, we see real coordination. Let's just first check the unit cell. So one of the atoms is located in in the corner, and two of them in their on their on the surfaces in the middle. So we can go to the unit cell and see its parameter. You see one of the gold atoms is located in the corner, and our three others are located in the middle of the plane. So and zeros show that it's on the plane. All right. So and this is a cubic. It's cubic um, cubic unit cell, which has A, B, C parameters similar and all angles 90 degrees. So in order to see the coordinations, we go and increase the unit cell by adding one more unit cell and on each axis. So, and then we'll examine it, and we can see that each gold atom has 12 neighbors. This is the first example. And another example of the cubic symmetry is our carbon diamond structure. We already talked about it in the first lesson of on SageMD. So diamond has also cubic structure, but now we see that it has 8 atoms in the unit cell. One of them again in the corner, 3 of them on the surfaces in the middle, and 4 inside. But they also in a special positions, which you can see if you go to the unit cell. You see that so one of them, this is the center, but others they are on a quarter, and that's what actually reflects the symmetry of which is reflection of the cubic symmetry. So their unit cell with a cubic symmetry, they have several planes, symmetry plane, several axes, which are two-folded, three-folded, and four-folded. So which is obvious by looking on their on the structure. So for three-folded axis, so if you put it in the corner and bring the line connecting to this opposite corner, so we'll see that it's will create their threefold symmetry. All right, so let's go to the example, last one in a cubic symmetry, and it's iron. Iron has only 2 atoms in a cubic cell. One is on the corner and one is in the center. So in order to understand its coordination of each atom, so we go again to their to the unit cell and build a supercell larger size, and then you will see that each atom has 8 nearest neighbors. All right, so next example will be monoclinic structure of sodium 3, aluminum, fluorine 6. It's a cryolite structure. Okay, let's open and see. It's quite nice structure, by the way. So first of all, let's see their the parameters of the monoclinic structure. So if we go to unit cell, we'll see that all A, B, C vectors are different. 2 angles are 90 degrees, and one is not 90 degrees, but actually in this case it's pretty close. So this is what is monoclinic structure is. So by examining the unit cell coordination inside, we'll see that the aluminum atom has 6 close fluorine atom, and it's form aluminum fluorine 6 anion with a charge -3. So in a balance of 3 positive sodium atoms, and in this form of monoclinic structure. That's another example. So let's go to see one more example. And in this case, it would be black phosphorus. Yeah, that's, let's see what type of the unit cell it is. And it is orthorhombic structure. Orthorhombic structure has all different A, B, C parameters, but all 90 degrees angles. So what we can see that it has bunch of planes, symmetry planes in the structure. So again, same as in previous case, in order to see coordination or chemical bonding inside of the crystals, we go again and increase the cell in order to see more clear the chemical bonding. So if we increase the cell, we see that structure is actually quite interesting. It's formed by polymers made by 6-membered rings, where each phosphorus has coordination 3, and then it form layers of such polymers. So that's what you can see, and each layer connected to each other by van der Waals forces. So that's how their black phosphorus is made. All right. So one more example. This time is a neighbor of phosphorus in a periodic table in the group 6 is sulfur. So, and let's see what kind of unit cell it has. And it has hexagonal structure. Hexagonal structure mean that we have 2 parameters A and B equal, C is different. 2 angles are 90 degrees and 1 angle 120 degrees. So that's how their hexagonal structure is made. So if we look inside, so even in one unit cells, we can see that sulfur make 6 coordinated molecules where each atom of sulfur is connected to 2 neighbors. So just to confirm this, we can just go and increase the size of the unit cell, again, as we always do, just to confirm our observation from one unit cell. So we'll see that sulfur makes 6-member ring. So there is another structure of sulfur which has 8-member ring. So that's a typical for type of structure sulfur. Well, now let's see what kind of structure is formed by its neighbor in in the same group but lower, which would be selenium. Selenium also has a hexagonal structure, which you can see just observing it, but we can also check it. So let's see what it is. Yes, so it has A and B the same. C is different, 90 degree and 90 degree 2 angles, and 120 degree the third angle. So since the atom has only 3, the unit cell has only 3 atoms in a unit cell, we cannot make an easy guess how it formed the chemical bonding. So, but we can see that two atoms are located on the plane, this one and this one. If we want to check it, we go and see the coordinates, and we see that two atoms has one of their parameters 0, which means it is in the plane indeed. So now in order to see the chemical bonding, so we go and increase the size of the cell. And now we see that in our chemical bonding is for selenium is similar for sulfur. So each selenium atom has two neighbor chemically bonded, but instead of making rings, it's create their the long polymer chain along one of the axes. And yeah. And finally, their final example of tetragonal structure. And in this case, as an example, yeah, I'm using zirconium silicate, which is called zircon. So zircon has tetragonal structure. Let's see what it means. Go and see the unit cell. And it's whole, their tetragonal structure has all angles 90 degree. Our two our unit cell parameters are equal and form a square. And a third one is difference. So that is called tetragonal structure. So by examining the structure again, so we can increase the size of the unit cell, as we usually do, by adding one more unit cell, the structure. So, taking a look at the structure, we can see that the yellow silicon atoms are 4 coordinated. Each oxygen is 2 coordinated. Actually, some of them 2, some of them 3 coordinated. And their zirconium has 6 coordination. So what you can do, you can continue your exploration of the crystal symmetry by using the big database in the SageMD program. So you can see how the chemical bonding is made inside of the crystals and what the symmetry of crystal is. So I think it's pretty interesting game, and it's enjoyable, and also you learn quite a bit. So in order to learn more about the symmetry of crystals, obviously you need to read special literature and watch some more movie. Enjoy yourself. Thank you.